Good morning, good afternoon. Thanks for attending this interesting live webinar on geothermal energy. We will be discussing the importance of geothermal energy, main regions with opportunities, how this energy works, the different systems and its challenges, and how we can model and optimize this process, showing some cases, studies, and examples. My name is Victor Salazar. I am the Regional Director for Latin America and the Caribbean. I have been working for CMG for about 27 years. Before I introduce our speaker and start the webinar, we have prepared a poll. I invite you to participate, either scanning the QR code that you're seeing on your left or through the website that is on the slide. So the question is, what is the main reason you think geothermal energy has not been largely developed? And there are 4 options. So probably high technology requirements or uncertainties related to the physics and operating strategies, high installation costs, and unclear government rules and regulations, or some of them. So I really encourage you to participate. That's good. We have started the answers. Seems that our attendance is inclined to the high technology requirements, and the first 3 is almost high. That's good. Carlos is going to talk about it a little bit, and actually we will see during the webinar part of the challenges that are required on this kind of energy, geothermal. I'm going to give you probably 1 minute or so to answer. High installation cost. Yeah, that's correct. Government, yeah, high installation, government regulations and rules. Okay, so 30 seconds more to go, and so we can start the webinar and answer some of these questions. Okay, we have started the comments in our LinkedIn chat. Okay, I think we can start now. Okay, so our speaker is Carlos Granado. He is going to explain most of these questions and challenges. Carlos is the manager for Argentina, Trinidad, and Venezuela for Computer Modeling Group, and has been with the company for the last 18 years, working in different areas such as training, support, consulting, and during the last years in business development of the company. So please post your questions in the chat that is active for this. We will answer as many as possible at the end of the webinar, and the ones that we cannot answer due to time constraints will be addressed directly afterwards. So Carlos, the floor is yours.
Thank you very much, Victor. Thank you everyone for attending to this interesting webinar. This is a pleasure for me to share this space with you. As Victor said, we're going to be talking about unlocking the potential for geothermal energy. Looking at the poll and the answers that you have given, yes, you are correctly right. Depending on the region, some of these limitations are related more to the technology, or the high cost, or the unclear government rules, but we are going to talk later about that a bit further. So let's start this presentation with trying to tell a story of a growing renewable energy industry. Energy consumption is by far the biggest source of human-caused green gas emissions, responsible for at least 76% of the worldwide emissions. Within the energy sector, just heat and electricity generation is responsible for at least 32% out of these emissions. Carbon capture and storage has been largely implemented in many projects in the US and Europe and Canada, but this process is about disposing CO2, which is already in the atmosphere, and we need to stop producing CO2. And for that, we need to further implement renewable energies for reducing the dependence on fossil oil. The director of the International Energy Agency ascertained that the world is set to add much renewable power in the next 5 years than it did in the last 20 years. Some experts even predict that by 2024, at least 33% of the world electricity is forecast to come from renewable energies. Due to the pressure in decarbonization, government seems to be changing policies, and this is added to the significant decrease in the production cost that shows a clear driving forces for renewable energies to emerge. And an international agency report titled Renewable for 2022 examined the energy resources around the globe and found that the wind and solar production outputs are expected to be double during the next 5 years. Let's talk a little bit about the uncaptured potential capacity for geothermal energy. If you see the left side picture, you see that in 2021, we basically set another record year for the installation of zero carbon power generating technologies. But unfortunately, this hasn't been the case for geothermal energy. You see the added capacity in 2021 separated by any source of energy. We see that definitely solar took the clear lead in the increment by generating an additional 130 gigawatts compared to last year. Geothermal capacity grew importantly, but this added capacity was 90% related to the US growth. In 2022, geothermal added much lower power than it was expected from previous years. And if you compare the amount of money that is invested in geothermal compared to other renewable energies, you can see that geothermal received around 10 billion US dollars, while solar energy and wind energy receive over 130 billions each. So the question arises on why geothermal energy has not been developed. Some experts compare geothermal nowadays with the cell phones back in the 1990s. They were big, they were expensive, and only few people could afford to have one. But things have definitely changed on that sense, and we think this is going to be the case for geothermal energy as well. Each year, only in the US, geothermal electricity offsets the emission of around 4.1 million tons of CO2 in the atmosphere. So I think it is about time to talk about the agenda of the webinar today. We are going to start talking a little bit about an introduction of geothermal energy. Then we are going to show you some specialized geothermal examples that we have done in the last year. We are going to show you how easy it is to create a basic geothermal case. And to end up, we are going to talk about conclusions. So let's start to what is geothermal. Geothermal is an energy that is a type of renewable energy taken from the earth core. It comes from the heat generated during the original formation of the planet and the radioactive decay of materials. This thermal energy is naturally occurring and is infinite, as we say. The mantle of the rock is named magma, and in some spots, the magma can come close to the surface near the crust. This typically happens near tectonic boundary, which are the areas where most volcanoes and earthquakes are mostly to happen. And we'll discuss this a bit further later on. When the magma comes toward the crust, the rock and the water absorb the heat, and then it creates geothermal reservoirs. In some areas of the world, this heat can be produced, that is, that they can be extracted from the rock and the water. Some studies ascertain that the energy present in the upper 10 kilometers of the Earth crust is basically sufficient to provide global energy to approximately 200 million years. So this is the energy needed for our entire civilization. The technological advantage of geothermal plants might take us to a point where we will have able to put geothermal plants everywhere. But in this case, the Earth is in constant state of change. The Earth crust consists in these 15 to 20 tectonic plates. And the lines can be seen in this picture taken from the National Ocean Service. These plates can be think as a piece of cracked shell that rests in the hot molten of the rock air, and they snugly feed against each other. The heat from this reactive process with the planet interior causes these plates to move either close or away, and this movement is called motion or tectonic shift. With the respect of the locations, the limits of these plates where the magma can reach the surface form the geothermal reservoirs, as we said, and most of these geothermal reservoirs are found along the boundaries. And it's evident that the locations of the plants and development of plants goes along with the locations of these areas. Some organizations has accounted the number of plants as Think Energy, and they said that there are around 500 plants installed all around the world. In the coming years, I think this picture is going to change, and we are going to be seeing more of these plants located not necessarily along these lines, and we are going to be talking a little bit more about that in the coming talk. Okay, so let's continue our chat with the advantages and challenges related to geothermal energy. The first, as you said in the pool, the advantage is a high potential. The worldwide energy consumption is around 15 terawatt, which is far from the total potential energy available in the source. The current geothermal installed capacity is around 16 gigawatts, more or less, which represents just 5% of the potential, which is calculated to be in 320 gigabytes. There is a hope that the number of exploitable geothermal resources will increase in ongoing research and development in the industry. Just in the US, the Department of Energy ascertains that the potential for generating energy out of EGS systems is 100 gigabytes. That means 25 times larger than the current EGS production, and it might give power to around 100 million American homes. It is sustainable and stable. Geothermal provides a reliable source of energy as compared to other renewable energies. This is because the resource is always on, 24 hours, 7 days a week, and 365 days a year. It doesn't depend in any conditions on like wind and solar. It is reliable. Energy generated from this source is easy to calculate, and it does not fluctuate at all. This means that it can predict the power output from the geothermal plant with a high degree of accuracy. On the other hand, we don't have to invest a lot in the conversion of this energy into current, and we don't need to have big batteries in order to accumulate the power that it comes from the source. It has a rapid evolution for sure. There is a great deal of exploration into the geothermal energy at the moment, meaning that the new technologies are being created in order to improve the energy process. There are an increasing number of projects that improve the growth in this area. And with this rapid evolution, many current cons of the geothermal energy will be mitigated. There are some calculations that in the 2050, the geothermal potential is going to be around 50 gigawatts. We think this is a bit pessimistic compared with our estimations. There is in the challenges, as we saw in the initial pool of the presentation. Yes, you're right. There are high installation costs. As a matter of fact, the installation of a plant is around $2.5 to $5 million for a plant with a capacity of 1 megawatt. The exploration and drilling of new reservoir played a big role, driving the cost up to half of the overall cost of the project. As drilling of wells and water production injection of this project will indeed cause some changes in the initial conditions of pressure and temperature and stresses of the reservoir, we need to take into consideration the changes that we are going to be causing in faults near to the project, or maybe cap rocks, and we need to be certain that we are not going to be affecting the stresses around big faults or fill these faults with water that is going to reduce somehow the friction between them and cause the movement that we translate in earthquakes in the surface of the earth. So we need to be really careful in the way we apply the technology. Other than that, we have the possibility of having thermal short circuits, which is mean that the formation where we are getting the heat from can cool down, make it impossible to continue the operations. So we need to be aware of this in order to plan our projects and installations. The last, like the O&G reservoirs, the geothermal needs a specialized subsurface know-how to guarantee the proper management and monitor to enhance the optimum operational decisions and to procure the long-term success of the project. So this plays an important challenge for this type of projects. So regarding the classification of the geothermal resources, we can start with the conventional hydrothermal resource, which is similar to what we have in the oil and gas industry. You could have faulted rocks and permeables, which where we could inject or produce from. We have heat, water, and permeability present. We can produce hot water or steam, if it's the case. We can always mitigate the losses of potential in the plants by injecting some water to maintain the pressure. The second is the enhanced geothermal systems, which are taking a lot of lead nowadays in the industry. The permeability is not high enough in this reservoir, so there is hot, dry, and dry rock with no permeability. Because of that, you need to create some hydraulic fractures and injecting fluid and produce a fluid back to extract the heat. The EGS system have a higher uncertainty, as we have to make sure there is enough conductivity between the injector and the producer in order to have the water traveling from one point to another. And we need to be sure that the exposure time of this water is big enough in order to heat and to be produced. The last and the third category of the system, we are talking about closed systems. Essentially, in this case, the system is closed and it consists in recirculating the fluid. It doesn't have to be water. It could be any kind of fluid. And then it takes the heat out of the reservoir just by conduction. The closed loop, this type of technologies can take the advantage of the existing oil and gas infrastructure and rigs and completion rigs in order to develop these kind of multilateral wells that are part of these huge heat interchangers on the surface. It can be located everywhere. It doesn't need to be located necessarily in hot areas, and it still can generate a lot of energy in order to generate power. So let's talk about the risk factors associated with geothermal energy. There are many uncertainties related to the implementation of this renewable energy, and they are not necessarily related to technological risk. Political risk play an important role as they are unpredictable, and they might the priorities might shift depending on the policies and regulations. The regulatory risk, we know we might have some insufficient and contradictory policies in some places and with legal frameworks to apply this type of project. However, with the current benefits toward CO2 reductions in some countries, it has triggered changes in regulation. As just an example, the U.S. Department of Energy said that it intends to make a geothermal enhanced system a widespread renewable energy option in the U.S. And they even launched last year a geothermal power airshot, which intend to cut costs in the geothermal energy system by 90% by 2035. More recently, a couple of weeks ago, they are seeking the application of a generation of a fund in order of around $74 million in order to help pilot projects that can help the advances and commercialization of geothermal technology. On top of this, there are very important global initiatives such as a Global Geothermal Alliance that has gathered over 50 countries that are decided to generate feasibility for the geothermal projects. Related to financial risk, of course, the markets can be fragmented, inefficient. and we can suffer frequent changes on the currency. However, in the last year and a half, and no matter the commitment in zero emissions by 2050, oil companies has become an important source of financing, as they have seen the perfect opportunity to take their capital, know-how, and skills to invest and bring it into geothermal and green a little bit their portfolios. Regarding technological risk, is what we are focusing in, is our main area of expertise are related to really understanding of the uncertainties present in these resources to account for its capacity to produce energy. It also accounts for the optimal number of wells to enhance the potential and economics, the type of completions, the field development plan and operation strategy to guarantee the long-term success of any project. Let's talk a little bit about the physics. Physics of geothermal have many sides, and companies should count with the technology that can provide solutions to represent each of these phenomena. Fluid flow, the most of the fluid flow in geothermal in reservoir occurs in natural fracture present in the formation, and sometimes in matrices that are related to impermeabilities that are related to the metrics, and we need to account the flow and the correct representation between fractures and metrics in order to accurately represent the physics of the process. Heat transfer, conduction, convection, dispersion, contour flow. Wherever the geothermal system is natural or man-made, heat transfer is the most important phenomenon, and it will be critical to evaluate the amount of energy that can obtain from the source and the time of production strategy in optimum to take the best advantage of the resource. Regarding heat and pressure losses, wellbore temperature and pressure calculations are critical to estimate the correct and optimum condition that should exist in order to guarantee the minimum losses of energy when producing the water from the reservoir up to the surface. Geomechanics, really important. As you see, we can present some changes in the rock, like cause some subsidence, activation of faults. So we need to guarantee that when we apply our projects, we are not going to be causing any damages into any closed formation that might trigger some troubles in the future. Regarding thermodynamics of mixtures, it is really important to represent the water properties such as viscosity and density. And these changes when they pass through different phases from supercritical conditions to liquid due to changes in temperature and pressure. Also, water chemistry play an important role. It's being used a lot to find out the origins of the water, and also to account for any reactions that might occur in the subsurface that can cause the deposition or precipitation of solids that might affect the production equipments. Let's come now and talk about the risking of the geothermal projects. Drilling costs, as I said, are around 30 to 50% of the total development costs, and it might vary up to 25% in some cases. This is why it's so important to account to uncertainties present in the reservoir to evaluate not only the number of wells, location, fracture, if there are any, and also the possible operation conditions that might yield to the optimal advantage of the resource. If drilling is successful, then the reservoir must be tested in order to determine the magnitude and productivity and to understand the longevity. This will help us to generate the power plant's design and to know what type of plant are we going to be installing. Also, we need to be really aware of the type of fluids we are dealing with, because hot temperature, abrasive rocks, and corrosive environment located on the ground come with a significant unknowns. And we need to account for these uncertainties in order to select the right equipments and the selection of the tubing and the materials and production materials in order to take advantage of the heat and allow the less of the pressure losses of the system. So now that we have talked about the introduction of what geothermal energy is, let's go directly into business, and let me show you some specialized geothermal examples that we have prepared for you. Let me come out of this for a moment, and And let's set ourselves directly into this presentation. So we're gonna go and see the results that we have performed in our software. We are gonna use results graph in order to show you some of these examples. The first example is related to a standard geothermal system. In this is the typical system where we drill wells, producing wells to get some hot or water or steam out of the formation. Of course, there is a lot of uncertainty of the side of the formation initially, and we need to account for them in order to be certain that we are not gonna get into a thermal short circuit. So in this sense, we don't only not only take into consideration the locations of the wells for the production of this water, but also the optimum configuration and completion in order to allow the lesser heat losses from the bottom of the perforations to the wellhead of the wells. Also, we need to account for accounting for the uncertainties of the size of the of the source in order to evaluate the possibility of the impact of just producing the wells as they are, where we can have an amount of energy generated, or also what happens if we added some injectors into the system at some point and then enhance perhaps the amount of energy that can be taken out of the project. Even when we optimize the type of completions and the spacing and the rates of the wells, we can even increase the energy produced out of one of these wells in 25%, which means a lot in the sense of having a long-term project success. The second case we are going to be showing is related to the enhanced geothermal systems. As we said, geothermal systems, there are the enhanced geothermal systems consisting in adding some fracture in the reservoir in order to enhance communication between producer and injector. But there is a lot of uncertainties in how these fractures go because we don't know necessarily the stresses distribution of these formations. And then we need to be aware that to account for these uncertainties in where are we going to be locating this well, what rates are we going to be using, what happens with these fractures when we start changing the stresses of the formation. Yeah. So we came up with this case of a study where we evaluate the representation of the fractures by using our methodology of a tartan grid, and we were able to calculate or to estimate the optimum well spacing between the production well and the injector in order to avoid water to go directly in the plane of the fractures from the producer into the injector, not allowing the correct or the exposure of this or the heat interchange between this water that we are injecting and the heat of the formation. We came up with an optimum well spacing in order to guarantee that we are not going to be producing cold water into our systems, and also to account for the uncertainties present on the fracture system. With this, we were able to increase the energy or the temperature of the wellhead of the producer in around 15%. So this is a game changer in the project. The other case that we would like to present is the closed loop U-shaped wells. As you say, these closed loop U-shaped wells consist in the connections of two vertical wells with many horizontal multilateral wellbores, creating a closed sealed radiator-like system. The working fluid could be selected and added at the surface. It doesn't have to be water, and then circulated to harvest the heat on the air. But then the question comes in, what is the separation of these multilaterals, which is the optimal length of them. And for that, we use our tools in order to optimize the distance of the separation between these three U wells to account for the best use of the energy that is under the ground. We see that when we have a 20-meter separation, initially it doesn't affect too much the temperature that is going to be seen in the wellhead of the wells. But as you see, as the fluids and the conduction of this heat comes from the fluid to the formation, we end up cooling the formation and affecting the performance of the system. We found out that in order to keep us safe and be able to produce the largest temperature in the wellheads of the wells, we need to have the wells at least 60 meters separated to each other. This kind of guarantee that we are going to get around 15% more temperature than it was originally. So this is interesting for us right now. The second case is going to be related to the formation of scales. So basically, carbon dioxide is present in important quantities in the geothermal fluids, and when the pressure drops, the chemical equilibrium of the brine changes with some of the CO2, and because of this, it can generate super saturated calcites, and that will start depositing the wells, not only in the wellbore but also in the reservoir, and will affect definitely the fluid flow in the system. So we were able to model the experiments of the autoclave in order to represent the amount of carbon carbonate deposit, and we put it in a model, in a single well model. And you can see here in the top right of the screen that as time passes, there is a important concentration of carbon calcite deposit in the tubings and in the production equipment. As a matter of fact, if you compare the case where we didn't model any type of precipitation compared to when we model the precipitations using the experiment, the rates actually drastically are reduced because of the reduction of the hydraulic diameter, equivalent diameter, due to the solid deposition. When we use our optimization tool in order to find the optimum operating strategy, we found out that just by reducing the rate of production, we were able to avoid the formation of these solids in the tubings, which is a really interesting case to share. Yeah. So let's talk about this last case of a study. We are showing in this case CO2 plume generation inside the aquifer. This is a promising technology that combines geothermal energy, while at the same time we enable carbon capture and storage to safely remove some CO2 and capture it at the surface. Yeah. We use CO2 as a surface working fluid to extract the energy. This has several advantages over using traditional water and brine, as it has much kinematic viscosity than water or brine, and the mass flow through the reservoir are higher than those when you're using water and brine. The initial stage of this is called the CO2 plume generation. This plume generation, during the first stage, the CO2 is injected in the reservoir, displacing the brines and develop a kind of CO2 plume. This stage is crucial since we need to have the sufficient amount of CO2 in the reservoir to minimize the water upcoming in the producing wells. During this stage, the production wells are shut, and we are just injecting CO2 at a fixed rate. That this rate is usually coincide with the production rate when we start the geothermal process. For this case, we consider the stage, this plume generation stage, to be achieved when the production well regions have achieved a pore volume space saturated with at least 55% of CO2. So this is highly dependent on the formation properties like permeability, porosity, and the diameter of the production well. So we use our artificial intelligence tool in order to find out the optimum rate in order to be able to generate this plume. As you can see here in the picture, this is the location of the injector wells. In the left side, we are showing temperature. In the left side, we are showing saturation. When we see that we managed to get a saturation of around 50 to 55% around the well, which is good enough in order to guarantee the formation of the plumb and the displacement of the water out of the producer. So we also perform some sensitivities by selecting the opening daytime. And we saw that after 2 years, we kind of guarantee that the water was not in the wells anymore, and the production of the water is less than or the CO2 is around 94% or 95% of the production of the total production of the wells. Also, we can see that we still can get some interesting temperature in the producers after many years, which are this temperature is good enough like to get a lot of energy out of the CO2. And this was a really interesting project to show to you. So I hope you find it interesting too. So let's carry on with the generation of a simple geothermal case. I am going to show you here that you don't need to be an expert, a petroleum engineer, a geothermal engineer in order to generate a single geothermal case. You just need to do some clicks and then you have your initial geothermal model generated. Of course, you can always account for the uncertainties present on them, but let's just go into this and open a new case. So we open Builder, which is our preprocessor, and we select that we are going to be using STARS, which is our thermal simulator. We select a date, and we click OK. Right here, our model is empty, and we don't have a reservoir, a well, or anything, but this is easily fixed by using our process wizard. A process wizard has been largely used in other areas as an enhanced oil recovery, but in this case, we are going to go and select the geothermal model. The geothermal model gives you some introduction of what geothermal is, it's based on what we already talked. And then we can select into the options of geothermal well, a closed loop geothermal well with injection and production from the same well through tubing and casing, or a closed geothermal U-shaped well. Let's take a simplest case to show you how you can generate your geothermal model. This is easy. Now you can see here your geothermal reservoir property, thickness, size, lateral size, properties like permeability, porosity, the temperature, the pressure. So let's start just generating a case where we have the grid to the top of the surface, so we can account for the losses of the geothermal source up to from the ground to the surface. We can set a really low permeability in order to start with. We can add depth of reference of around 2,500 meters. We can generate, sorry. Okay, let's put the pressure of 900. We can show you here the thermal controls, thermal conductivity of the reservoir. We can select if we are going to be injecting from the tubing or from the annulus. We can select the rate that we are going to be injecting. We can select if we want to use some isolation. In this case, we use. And we can actually input the tubing information, the casing information, or we can select the information directly from the APA tables available in the software. Let's select a tubing of 1.5 inch casing. And let's change the reservoir temperature from 15 to 20. And now our model is pretty much set to be run. We finish. And there it is. We have our model built. We can go and have a 3D view of it. We can go in properties and delete the grid and create some transparency, and you can see your reservoir and your well. You can have a look at the well configuration by clicking here and see. Give me a sec. Configuration. And we can actually set our simulation to run by clicking some numerical control. Sorry, I'm having issues with my mouth here. We can select the auto tune in order to tune the artificial intelligence to run our software. So we are set, we save, we click a name for the model. We click OK, and that's it. We're set. We run the model. That is going to take, I don't know, some seconds. It's a 5-year model. So this is it. It's done. It ran in 15 seconds. So let's go and have a look of the results. That's it. Voila. Right here, we can see our model in 3D, the configurations of what we wanted to be modeling in this case, and the results of it when we start injecting at a temperature of 20 centigrades, and then how this temperature changes as the water is injected into the reservoir. Right here, we can see that at the end of the project, injecting a water of around 15 centigrades, with our configuration, the temperature profile goes up until the bottom of the reservoir, of the wellbore, and then goes up using the isolation and conductive information that we put in the steel of the completion. So at the end, we end up producing a fluid of around 73 centigrades, which is good enough to generate some power out of the binary plant in the case we want, or to generate some heat for direct use or something. So let's jump then directly into the conclusions. So geothermal plays a key role in decarbonization to reach zero emissions target. Geothermal is a reliable source of energy with new projects coming all over the world. New technologies are improving the overall cost effectiveness of the geothermal energy, and geothermal simulation can optimize projects to decrease their long-term value. So thank you very much for your attention. We might now get some questions from the audience.
Thank you very much, Carlos. Interesting topic. And we got lots of questions and comments, both directly at LinkedIn, but also direct questions and everything. So I think we will try to answer the ones at LinkedIn first. And if we have more time, then we will answer the others. So we have more or less 15 minutes. So the first question is a very interesting topic. Wouldn't you say that one of the biggest challenges to a large-scale use of geothermal energy for electric power generation is the low efficiency of geothermal power plants at low to medium temperatures, enthalpies, and very high flow rates required if temperatures are relatively low?
Well, of course, it depends on the amount of energy that you have in the ground. But yes, you are certainly right. It is difficult to get a high enough temperature in order to generate power out of any system, but there is technology available in order to use other fluids that have a lesser a boiling point than water that could still generate some steam to activate some turbines to generate some energy out of it.
The other question is, can CMG handle phase changes of CO2?
Yes, of course. Yeah, we have a full representation of the behavior of the CO2. As a matter of fact, we have been the tool that has been largely applied for and recommended in order to represent the CCS, carbon and storage, and its representation of all the type of trapping mechanisms that are present in this type of processes.
Okay. Any thoughts on how you could model geothermal potential from mature abandoned SACD projects?
Yes, as a matter of fact, because of the time, we couldn't show all the cases that we have evaluated, but one of the cases that we have certainly evaluated is getting this energy out of all mature thermal projects, not only in Canada, but also in South America. Like there is a lot of projects that have largely changed the temperature of the formation in the last years, and this heat is there, and we can take advantage of that.
Excellent.
And we certainly can model that using our simulators. Sorry.
There's a question here asking if we recorded this for future reference. I think I can answer that one. The answer is yes. Actually, we will be sending a link so you can see the presentation again. So no problem with that. Another question, do you have a real study case for the EHS to calibrate the simulation for the distance between wells?
Well, yes, we have worked with real data with some of our clients. Of course, there is a lot of. We are starting this process actually right now. We are developing the geothermal sources lately, and because of that, we have come with a lot of projects to represent all these type of phenomena. So we have real cases. Yeah.
Okay. Interesting question. Following one, similar to Toby's question, what do you think is the biggest challenge in modeling existing oil and gas reservoirs, wells, that could be converted to geothermal?
Well, I just think that there is a matter of changing the minds to have some companies that own these fields committed to try to generate an option, an energy option out of these systems. I see a lot of companies and OIG companies, as I said during the presentation, in the last year and a half has focused a lot of effort in getting into geothermal, taking advantage of the know-how, skills, and resources in order to make them feasible. So we have been doing some studies for some operating companies where we are taking advantage of this resource.
Great presentation. This person says that been following EGS closely and believe that they are poised for significant growth this decade. The question is how a star can handle different fracture shapes, dips, and the impact of temperature on performance results.
Well, as I said, we have been largely working with fracture reservoirs during the last 20 years. As a matter of fact, 30 years, we have developed a novel way of representing fractures by using tartan grids in order to account for all the interaction between matrix and fractures. We can use information coming out of the fracture softwares in order to use them in our simulation. But as I said, there is a lot of uncertainty related to the stresses in this type of reservoir, unless we are using data from the ONG industry that can lead us to understand more or less the fault, the location, the thermal, the amount of properties that are located in the reservoir. Other than that, going into deep geothermal hydrothermal resources is always an uncertain, because we don't have much data about the stresses on that. So that might make a bit more difficult to know how the fractures are going to behave in these systems. And this is why it is important to account for the uncertainties present of that in order to plan your projects and to guarantee that the longevity of the projects are taking into consideration these uncertainties.
Okay. What is the highest temperature for default fluid PVT tables in the simulator now?
Well,
Think,
I
think
might need to
probably,
come back to you on that.
yeah, asking probably
Yeah,
about a limitation on temperature or
yeah,
something.
yeah. Well, we might need to come back to you on
Yeah.
later on with that question. Yeah.
Great topic. Thanks for the great presentation. Does CMG have data about efficiency for these geothermal plants?
Well, we don't know that we are a company that develops software. The data belongs to the clients, and most of the time, this data cannot be used unless it is published somehow. As some of the data we use for example, for the CO2 plumb generation was come from a published paper, and in this sense, we could share that information. But other than that, we don't have data to work with of our own. It's data from the clients.
Think following question is more probably they would like to know your opinion. I would like to know more about the price comparison between the geothermal energy production and fossil energies. The question is possible in the near future replace the fossil energy with geothermal?
Well, we are going toward that. I mean, there is a commitment of having zero emissions by 2050, and companies seems to be taking it seriously. Even some companies that has no, some countries that has not necessarily signed the agreement seems to be moving forward faster than the ones that have signed it. Regarding the cost differences, there are a lot of information in the web, and let's say that the cost of generating energy out of geothermal is equivalent to what it is to generate the fossil. We are not going to need to switch anyway, because at the end we have a commitment to generate zero emissions. So answering your question, yes, there is a potential. There is enough energy, as I said, within the first 10 kilometers of the aircraft to generate energy for many years. So yes, we can displace the fossil fuel generation with geothermal for sure.
Another question, Carlos. Thermal conductivity is a function of temperature, fluid type, fluid saturations, porosity, effective stress, etc. Could the
Mm-hmm.
user define a functional relationship for thermal conductivity in the simulation, or is it assumed to be constant for each grid block?
No, I think that it is a possibility of generating to adapt the conductivity to the parameters that you have mentioned. As a matter of fact, this is a strength of having a reservoir simulation software that is dynamic. Basically, it takes into consideration all the properties that you have mentioned in order to accurately calculate the conductivities of the system. So.
Are the cases you shown available in CMG package?
I might need to check that. Some of them are based on public data, and I'm sure we could share them. Some of other are more related to clients, and we might not be able to share it. But if you contact us directly, we might be able to evaluate what of the data presented in the webinar can be shared with no issues related to confidentiality.
I think we have time for a couple more questions, and then we will leave the others to be answered directly afterwards. So thank you for your presentation. We talked mainly about the risk associated with the high enthalpy systems. How would the risk of low enthalpy systems compare?
Well, this is a difficult question to answer right away. We will need to do some more calculations and studies in order to account for that. But the uncertainties remain the same for both of the systems. I mean, Some of them are related more to conductivity because it's the most important. Some are more related to convection forces or even to counterflow because of the movement of the steam and water inside the reservoir. So I wouldn't know how to answer this question right straight away. So
Need more studies, yeah.
yeah.
Are there any real life examples of closed loop systems?
Yeah, there are. I mean, some companies have largely developed these closed systems, and you can find them on the web. Some Alberta companies are really advancing the process, and either in some other countries and some other um, areas of the world. It's just a matter of looking for data and publications that are available right now. Is on the other hand, it's not that to model. It's just a matter of understanding that these are just like big radiators or heat interchangers that we are developing under the ground. You can always model that in the simulation. The question comes to, is it possible to do it in real life? And somehow we have seen real examples and pilots of the application of this type of processes. So that's why I said in my presentation that geothermal is gonna have a big turn in the coming 5 years, not only because of the investment that is being given to the technology, but also to the advances of minimizing the costs. And this is going to be a point, as I said, when compared to technologies as the cell phones in the 1990s. In 10 years, we are going to see a lot of geothermal projects coming forward around the world, and a lot of generation of geothermal energy is going to come into our world. I think that even this 50 gigawatts estimation that we have for 2050 is going to be lower than that the reality. I'm pretty sure of that.
One more, and I think we're done. We don't have time to answer all of them. What is the most critical information needed in the reservoir to evaluate EGS, in your opinion?
Well, there are many factors. Stresses distribution, because you are going to be fracturing the reservoir. Then you need to see if these fractures are going to be expanding because of the thermal stresses. When you cool the rock, this is going to be it's going to have an impact in the stresses and might open or create a preferential path inside the fractures that might end up causing that the water is going to travel from the injector into the producer without having enough time to connect or to interchange heat. In the other hand, there are many uncertainties related to the type of completions, the distance, the optimum distance between wells, the amount of energy you might end up getting out of the system. But we have seen real cases around the world of application of these technologies, such as Cornwall in UK, which is a huge project that is being implemented, and it's going to be giving power to many families and homes in the UK.
Okay. Okay, thank you very much, Carlos, and everybody who attended. We didn't have time to answer all the questions, but we will answer them afterwards directly to you. Thank you. Thank you, Carlos.
Thank you, everyone, for attending to the webinar. And thank you, Victor, for the help.